So today I'm going to talk about spin glass. So I'm going to continue what Igor did in the lecture. So I didn't write any tutorial notes for this tutorial, but I'm going to follow lecture notes of my former advisor, so I put it on the Moodle. So this is going to be like more or less the structure of the tutorial. The notes are a bit more detailed than what I'm going to do because it contained like 3 full lectures and I only have 1. So we're going to skip a lot of like calculations and stuff. So we're going to work our hands a lot. So in general, we're going to talk about the concept of disorder. So we have an Hamiltonian that looks something like this form. Of course, we can have like other types of disorders. So we talk about spin glass. It's obviously not the same as like regular glass. So in the case of like regular glass that we know from windows and stuff, we have like a disorder that comes from like the structure, like the atoms. And here we have disorder that comes from the magnetic couplings of the spin. So when we have a random distribution of this coupling constant between the different spins in the system, we don't necessarily have disorder that is like interesting disorder. So this is connected to something we talked about earlier in the course, which is frustration. Probably going to have the title, so okay. So when we talked about quantum ensembles, I think maybe, if I look at a system with, let's say I have 3 spins, so I, J, and K, and I have different coupling constant for each one of those, between each of those spins. So let's say this can be like either magnetic, ferromagnetic or antiferromagnetic. So if all of them are ferromagnetic, so this is and antiferromagnetic will be A. So if everything is ferromagnetic, then if this spin have, so if this one is plus, then this one also want to be plus, and this one also want to be plus. So ground state is very trivial. But if now this one going to be antiferromagnet, so now if this plus, and so this one also want to be plus, and this one also want to be plus because this is ferromagnet, but now this one want to have like, the word want is not exact, but you understand. You want to have like opposites direction for the spins because of the sign in the Hamiltonian. So if you remember, just ferromagnet, I have something that go like minus J S I S J, and antiferromagnet I have plus J S I S J. So if I have a positive coupling, positive sign before the coupling, I'm going to have opposite direction of the spin, and I have the same direction of the spin if I have a minus sign. So this is ferromagnet and this is antiferromagnet. if I have, so depending on the different interactions in the system, I may or may not have frustration in the system. So the cases where I do have frustration will be if if we define antiferromagnet as a minus sign and ferromagnet as a plus sign. So we have frustration if the multiplication through all of those different interactions is negative. So what does it mean? So if everything is plus, then I have a ferromagnet, a ferromagnet, a ferromagnet, everything is fine. If I have two antiferromagnets and one ferromagnet, then those are going to be identical because of the ferromagnet, and this one going to be different, but this is okay because this is aligned with what this coupling wants and what this coupling wants. So those are opposites and those are opposites. And then the multiplication will be plus, minus, and minus. So this is plus. If I have two ferromagnets and one antiferromagnet, then I have overall minus sign. So I have frustration because those two are not going to match. So this much here. And also if I have only antiferromagnets. So those want to be different, and then those want to be different, but those two match. Okay, so this is the concept of frustration, and the way it relates to disorder is if I have such a thing in the system, then I'm not going to have a well-defined ground state to the system, because the system is going to keep flipping between the different sides, because I never have a state where like everyone are happy. So let's look at this type of system where I have disorder, but I'm not going to have frustration. So I think it's called lattice. Yeah. So lattice model. So Jij equal to AI Aj, where for each of the spins, where AI or J equal to plus minus 1 with equal probability. So P plus minus equal half. So half the time it's plus, half the time it's minus. Then the Hamiltonian will be minus AI, Aj, sigma I, sigma J. I'm ignoring units. I don't define the units of A. So this is like a very simple example for random coupling. So first of all, let's see what's happened here. So I have AI, Aj, and K. So if Aj, let's say, equal plus, AI equal minus, AK equal plus, then this one going to be plus, and then minus, and then minus. So overall, the multiplication is plus 1. Now if I'm going to change one, so let's change this one to minus, for example. So now this one is minus, and this one is plus, and this one is minus. So still the multiplication is 1. So it's easy to show that for any case, I'm always going to have a system without any frustration. So if you want to solve it, there's like a kind of simple transformation that people use to solve it, which is I can define like a new variable, like sigma tilde or something, that is AI sigma I, and then the overall Hamiltonian is just sigma I tilde, sigma j tilde. And because both AI and sigma I can be either plus or minus 1, then this one also going to be plus and minus 1, then this transformation is valid. And you see that this is...
Shouldn't be minus? Minus that shouldn't be?
Yeah. It should just have to be consistent. Yeah. So this is just the usual Hamiltonian, and then like you see that this is like a fake disorder. So it doesn't give me anything very interesting. Okay, so the question is, when do I have a real disorder? So the model for spin class, there are like a bunch of different models for spin class, but I think the usual one, the more common one, called Sherrington Kirkpatrick. I don't know how to pronounce it, but it's usually called just SK. So, okay, the Hamiltonian is still the same Hamiltonian. Just skip it. And then the coupling J is being taken from some Gaussian distribution. So, specific value of J come from what's the normalization? 2 pi over n. So this is for specific value of J. So I have one system, and in the system I have different couplings, and overall I have n couplings in the system. That's it. So overall, the distribution for I write it as P of J will be a multiplication of the different probabilities for each of the couplings. So I have a product of pi over n to I to n stem. Let's say okay, so yeah, so the product is for I smaller than j. So for each coupling system, yeah, so this is just the product. We don't care about the indices. Okay, so this is so we actually what we did, we introduced a new random variable to the system. So we have two ways to approach the problem. So one way is when we calculate the partition function. So one way is to look at just random variable within the system, and then we average. So let's define this form of average, like with brackets and j, as average over j, which means I have. So if usual partition function will be, I have a summation over the different spin minus beta h just minus beta h. So this is the usual partition function that we know from everything. So now we have a random variable, so we say, okay, let's average over j. So now z is equal to, I have an integral over d j I. Okay, I leave it in summation. So I have p j I j, and then z j, then add the sum of sigma k. Okay, this is just average over the variable. So this is one way to do that, and then if I calculate the free energy,
What's the index of the sigma?
sigma k.
K? Okay.
Yeah, this is like the trace that we take. Maybe sum over all the different states of the state.
Okay.
So we calculate the partition function for specific realization, and then we average over all of the different possibilities of j. So if this is the partition function, then the free energy is minus kBt, and then log of z, which is the average z that we found. So I write it big. So this is one way to do that, and that's called a need. So I'm going to write the two ways, and then I'm going to explain the actual difference. Another way is to say, so the energy is an additive quality, which means that like it depends on the size of the system, right? The bigger the system, the bigger the overall energy. So instead, we can average over the energy, not the partition function. And then what we're going to have is f is equal to average minus kBt ln of z, and then kBt is just a constant, so this is minus kBt, and then average over the logarithm, so ln z with respect to j. So I'm going to have again the same thing here. So the only difference is if I'm putting the average with the over j inside or outside of the logarithm. So okay, so first of all, one difference is that you can either see that, and if you not see it now, you'll see it later when we do the calculation, that this option is much easier to calculate because the exponent here is going to be much easier than the logarithm of the full partition function, because this summation is now inside the logarithm. So this is going to be very horrible function to average over. So the second option is much more complicated. The physical difference, which is the important one, is that, okay, we call this a need, this is called quench disorder. which the meaning is like frozen. So the meaning of the first option is if you think about, let's think about like actual glass, because I don't know how to imagine spin glass. So you have like one system, and you say that like the different small parts in the system, each one of them relate to like different distribution of J, and then the overall system, the qualities of the overall system given by averaging over all of those small systems. And then in the quench disorder, I say I have one system with specific distribution of J, and then I take multiple systems and average over those. So it kind of sounds the same, but it's like okay, think if you try to if you think about like averaging over like something like, I don't know, weight of a person. So you have like one person, and you have like weights that fluctuate over time, and then you can calculate the average weight of the person. Versus if you want to think about average height, so this is something that usually doesn't change, so we have to take a lot of people and average over those people. So usually people use this option when you have something that's dynamic. So you have the distribution of J change with time. So I take one system, and within this system J change over time, so I have to average over that, versus something that's frozen in time. And then if I want to look at an average, I have to take multiple systems and then calculate the qualities of each of those systems separately, and then take the average. So usually when we look at most of like spin glass typical systems, we want to look actually at that quality, because the time scales of the change of the couplings behavior is actually very, very slow compared to the time that we measure. So this is much more realistic. Questions? No? Okay. So, okay, so we have two ways to calculate the average, and we agreed maybe that this one is the one that we want. And we also agreed that this one is is harder to calculate. So now we're going to use the title of this class called replica theorem. Yeah, okay, I will just rewrite this later. So replica theorem or replica trick, depending on how fancy you want to sound, it's basically say that we said that the average over the log of z is something that's very hard for us to calculate. So instead, we claim that the average over log z is actually equal to the limit of z to the power n minus 1 over n, where we take n to 0.
Oh, so that average?
With that. So you can basically prove it by you have everything in the notes, but I don't think it's very important. But you put that in like exponent of a log, and then you expand the exponent to Taylor series, and then you take this limit, and you get those two give you the same thing. So this is like an approximation or assumption that's surprisingly seem to work. So instead of calculate the average over the log, we calculate the average over z to some power n. So the reason it's called replica is because, like, if Z is the partition function of one system, so you have like n replicas of the same system. So what we're going to do, like, in the end of the tutorial, is see what happened when we compare different replicas of the same system and how different they are from each other, which is the thing that's defined the behavior of spin glass eventually. So let's look at like a simpler example. Okay, so before we solve the actual system that we want to solve, we're going to look at the solution of that system. We're not going to go through all of the solution because it's a bit complicated, but just the general idea to understand how that's going to look. So we have, the system is defined, so we have n particles. We look at like, we define 2 to the power n states, so actually 2 to n particles. The reason, so when I looked at the thing, there is a specific reason why to define 2 to n and not n, but it's like, it's very arbitrary, so that's not important. So we have some number of states in the system, and each of those states have energy ei, where I go from 1 to 2 to the power n, and the distribution of ei is also, surprisingly, taken from Gaussian. So let's see what's happening. So if you calculate so the reason people like this model, because you can actually calculate the energy exactly, and if you do it, you will find that the free energy equal to minus j square roots ln 2, so just a constant where the temperature is smaller than some critical temperature, and minus t ln 2 minus j square over 4t, so some function of the temperature where t is larger than the critical temperature. So with the temperature is low enough, we have something that is like a constant. So this is like the ground state of the system. So if you compare it to like the Dyson model ferromagnet system, where we have the disordered and the ordered states. So you have like the discontinuity in the behavior of the free energy when you go above some temperature. So basically you have some type of phase transition. So if you go now and you calculate and you want to calculate the free energy via each one of the methods that we saw. So let's do in both ways, the annealed version and the quench version. So Z for one realization. So this is equal to average over E minus beta E or beta H beta E. And then the average, so we have two n states, and each state have taken from some distribution. So we have product of two n integrals. dEi p of dI, which is Gaussian. Let's use different index. Okay, so you have two n integrals, and you actually can solve it from the symmetry, the symmetry form of those integrals. But if you have the patient, and eventually what you get is that this is equal to 2 to the power n, and then e to nj square t square 4.
Isn't the integral normalized? Just shouldn't this integral be just 1 because it's
but this is inside the integral. This is
okay.
the brackets are for the multiplication for the product, but you integrate over that. Yeah, sure.
What's in the denominator?
What?
Next to the t squared?
Yeah, this is. Let's put it here. So
4.
nj square 4 t square.
Right.
Yeah. So if we take the calculated free energy, so F yield is just minus kBt, and then ln of what we just calculated, which is going to give us, so n ln 2 plus nj square. So this is the free energy, and you can already see that this is just a continuous function. It doesn't have anything that exhibit any type of behavior that's similar to what we would expect from the exact solution. We cannot find any type of phase transition here. So you already see that this it's, at least for what we are looking here, this is not going to give a very good description. So let's try instead to look at branch one. So we calculated the average for z to the power 1. So let's do instead z to the power n to do the first step in that type of calculation. And if you do that, which we will not do, so this is going to be basically the same integral. So we have the products from 1 to 2n. And then we also have the products of the different partition functions to the power of some n. And this is all very forward. And if you calculate all of that, you eventually get that this is equal to 2 to the power n so we have m different summations. So m1, m2 until n1 n2 until nm, where m the number of states, so let's just call it 2n. So n factorial, n1 factorial until n factorial. An exponent of n beta square over 2. Yeah, this is not a very useful expression, so feel free to just ignore it. Just need to make a point. I think this is a point. Okay, something like this. It's not important. Anyway, the point is, eventually, if you go through the calculation and you're able to take the limit and go to 0, what you're going to see, I really think you can more do it like you can do it more like numerically. You're going to get something that's give you this transition that you would expect here. So it's not very clear to see, and in that case, actually, what this is actually more complicated calculation than the exact calculation. But yeah, this is just to see the way that it works. So the point is that where you have something that's you have qualities of the system that only can be calculated really from the quenched or the quenched disorder or the quenched type of calculation. It's called self-averaging property. So this is going to be for stuff like so we said that the free energy is like the energy in general is like an additive quality. So it depends on the size of the system. So this is going to be for the energy, for the free energy, the entropy, volume, also specific heat. So all of those stuff relates to that type of calculation. Okay, so let's go back to what we wanted to solve. So I'm going to ignore constants. Okay. So now if we want to calculate the free energy, so J is, for specific values we say this the distribution given by that. But in general, J is like it's like a functional. So I'm going to use like a functional integral. You know, like when you use that syntax. If it bothers you, it doesn't really matter. Just you can't use like regular integral because J is not like a variable. It depends on the other stuff in the system. So like it depends on the coordinates. So I'm going to use that. So we have P of J. E minus, and then the Hamiltonian beta okay, so this is what we want to solve. So I forgot the lamp, right? Yeah, I didn't want to write it like that. So this is what we want to calculate. So if we wanted to calculate the annealed one, then it will be the same way that I originally wrote it wrong without the lan. And then what we're going to have is we have a summation here with the something that's linear with j in the exponent. And we have the multiplication from p with something that goes j squared in the exponent. So if I put everything together, I get something that's that just looks like a Gaussian integral, basically. So if I don't have this line here, and then it's something that's basically solvable. But because I have this log here, I cannot move stuff around. So this is what we're stuck with. So what we're going to do is to use what we did here. So what we're going to do is to calculate the n replica partition function and then take the limit of n go to 0. So the n is the j So this is the n replica. And very important point that I forgot is the Hamiltonian here, which relates to the specific model. This is a mean field function. So we sum over all of the different sides in the system. And so this is very similar to what we saw when we did like mean field with like normal ferromagnet. There we just had a constant j and it was outside. So basically a lot of the stuff that we're going to do, like a lot of the stuff that we are not going to do because I will skip it, are very similar to what we did with normal mean field, like the Hubbard-Sotonovich thing when we use the Gaussian integral and the Sadler-Equal approximation. So all of those stuff. So except of the notations are a bit uglier and the calculations are a bit more annoying, but the general concept for that stage is very similar. So Okay, so we just need to keep track on the different summations. So we have this summation over the different sites in the system. This is the summation over the different states of sigma k, and this is over I think this will be over k for the different no, sorry. Which index did I use? Yeah, okay, in the notes there is some, I think there's some indices that repeat themselves, but I think they should be k. So this is also for the different sides. Okay, let's be consistent. Okay, so basically I will skip a few stages, but what we do is we take the exponent n, and instead of that we just write it as multiplication of n states. So we have like something like that to go until n, right? Because if they are all equal, this is equivalent. And then we put this product inside the exponent because we have an exponent of a sum instead of product. And then what we get this is eventually sum over sigma I k. So we took this summation out, an integral over dj, and then an exponent minus sum n over 2j squared. So this comes from this minus beta sum over k. So this comes from this, from the different replica, and then sum over I smaller than j, j, sigma I, sigma j. Okay, so now we have something similar to what we wanted from the annealed version, which is we have an integral of an exponent, and all of the terms in the exponent are fairly simple. So we have something that's linear with j and something that goes like j squared. So this is something that we practically can solve. So if you refer to j as just like a variable, so this is just again a Gaussian integral. And this is going to give us sorry, there is also k. So those have like two indices, ij and k for this summation. So this is equal to the sum exponent beta square to n. So what happened is that we just got rid of j. So this is like a Gaussian with sigma and sigma j. So okay, so now we would like to. So if you remember, it's that. So if you remember at that point when we did the ferromagnetic model, we had something that go like a sum over sigma I, all of that square. And because we don't know how to take the trace of that, we use the Hubbard-Satonovich. So we write we write this like Gaussian form, not Gaussian because it's not a minus, but like something that goes like an exponent of something square, or something that goes as an exponent of something that linear with that term, using a Gaussian integral. So if we do that, we can do basically the same thing here, but there is something tricky because if you see, we have like yeah. So we have this summation inside the product of the square. So we actually have to define n different variables that each correspond to one of those integrals. So we have multiplications of integrals, and this is going to give us, after playing a bit with the summations again. So we have an integral over so we define a new variable q that depend on two indices, a and b, and I'll show in the second wire. Okay.
Integral, right?
Yeah. Okay, so just a quick. So here we had the summation over the different replica that depends on k, and the summation over the different sides of the system. So you can move from here to here, by just playing a bit with the indices, but it's not important. But we can rewrite that in a way that we had two indices that represent different replica, and one index. Sorry. No, it's not. Yeah, okay, forget what to say. Okay, so we still have. Okay, I want to keep the notation of the indices, so I apologize for the confusion. But okay, we still have the summation of the replica, but now we represent it with I, and AB will be the index of the new variable. So the change we did relates to this correlation here. So we just changed the notation of the indices. So this is not. Okay, so. If we usually introduce like a new variable, I think it was the y when we did like the regular main field, and then we had an integral over y, and then here we just would have y, and here we have y squared, and without the second summation. So here because we have basically for each replica of the system we have one variable. So the meaning eventually of what that thing is going to be is a variable that's compared between two different replicas of the same system. So A and B would be like the comparison indices. So yeah. So when we did the saddle point for the ferromagnetic case, we had something that go like remember something that go like an integral dy y, and then this would be the free energy. Relate to the order parameter y, which will be equal to m, which will be equal to the average spin. So what we want to do here with that whole expression is to get to something similar and to define a new order parameter that also relates to the different states of the spin of the system. But unfortunately, it's going to be a bit more complicated. So, if we, alright, I apologize that I have to skip over so many stuff, but otherwise we'll just be here until midnight. But basically, we can find the value of the order parameter q. So q and b will be defined as a summation over I of sigma. If you want to like minimize everything here, like we do with the free energy. So this will be sigma I, sigma j. So sigma I for A and B. And here, for those who looked at the notes, there is a mistake in the notes. It's put like different indices, like I and j here, but they both should be I. So the meaning of that variable, instead of looking of the summation over all of the different spins in one system, we have 1 over n of course, I look at the same spin, a different replica. So this is like replica A and this is replica B, so I take like two like windows, I don't know, and I look at the same spin, the same location and I compare I look at the correlation between those two spins. So if all of those spins will be, if all of those states will be identical, then we expect this to just be equal 1, because they will be like strongly correlated, and then if they're completely not correlated, this one going to 0. So this what's defined to be the order parameter for such a system. So it's not, maybe not super intuitive, but okay. So following that definition, we want to rewrite all of that as something that basically looks like that. So I'll just write it in more. Okay, we see that we basically have something inside the exponent, but this expression is a bit ugly. You can basically, you make some of the summation into a product, and then you take the log of the exponent, you just move around stuff a little bit. It's really not that important. And then what you're going to get is eventually that this is equal. So I still have the product of the integrals, Q, and then an exponent of, so those two stay the same because they're already well behaved. so you see that we move this sum into the exponents. We changed a bit the order. And basically, what we have now is something that we have the n, which is the number of particles outside of everything else. And then remember when we use the saddle point, we said that we have an integral over a function with maximum, and then when we increase the size of the system, this becomes more and more sharp, and then we can only acknowledge we can only take the contribution from this point and we ignore everything else, and this is what gives us the minimum of the free energy. So this is what's going to happen here. We have the contribution of n. So basically all of that is equal to beta square and n f of q. So I can copy that, but you know. So the free energy is basically everything that I have here divided by that. Okay, so we have an expression for the free energy, but it's still very ugly.
Don't think the beta should be squared.
No, this is fine. We will handle the square later.
Yeah, but when you write the free energy, it should be with one beta outside. As you wrote above.
You talk about that.
Yeah, as you wrote above. Since the free energy is F.
Yeah, you are right. I don't know why I wrote square. Yeah, I got confused because this one was square. Yeah, you're right. Okay. Okay, so basically what we want to do now is to find explicitly the expression for the order parameter, right? The same way that we found the average magnetization in the ferromagnetic case by minimizing the free energy. So what we want to do is to solve that. So okay. So far this was like the more technical part. So if you lost me, this is the time to come back. So here enters the important assumption that we make, that is the replica symmetry assumption. So the assumption says that the variable QAB is equal to some constant Q, where A is different than B, and 0, so and 1, where A is equal to B. Well, the first one, A is not equal, yeah. So it basically means that we said that A and B are different replica of the system, so they're like different copies of the system. So this just means that the system finds stable state where like all of the different replica of the system basically going to look the same, right? If I look at the same system, this is just the correlation is just going to be 1, and if I look at different system, they're all going to behave in the same way. The correlation is always going to be some constant. So I'm not going to have a difference between the different systems, basically. So that's therefore the symmetry. So under this assumption, we can very much simplify the free energy that we get here, because this summation is going to be trivial, not trivial, but a lot simpler. So okay, so if we look at here, for example, I will not Do you ever see anything? So this is similar to what we did for minifield. So this is basically like saying half of the summation of just A different than B, right? This is the only difference if I take A smaller than B or just A different than B, which is equal to summation over all A and B minus the summation of A equal to B. You remember this is how we started the mean field thing, and we got that this gave us like a constant, and then we ignored it and everything else. But what we get here is that this one. So we have summation basically of A and B. Q going to get outside because it's a constant, it doesn't depend on A and B.
Yeah, but it's a constant only if A is different.
Right, but for
But here you assume
but then
A
you
and
take
B.
out A. Okay. Right.
Yeah, but when you
כן,
don't take it.
Yeah, so
כאילו אם לא מחסרים את זה, נכון.
Yeah, if you don't have the minus.
yeah, okay, so I don't think I actually need this. Okay, let's start them from here. Okay, so this is just half of A different than B, Q B square, and this is Q square over 2, and then we have the two summations, so one going to give us N, and one going to give us N minus 1. And then I have, I think I'm missing something here. Yeah, we're supposed to have N here. Okay, and then it's fine. So here, so this would be Q over 2. And then just sigma A. I think either there is a mistake here, or I forgot something. Okay, do you want to take a 10-minute break? Okay. Okay, so let's go back into 10 minutes, and I will figure out what's happening. stupid. There's no money here.
היה שבוע הבא יש הרצאה ותרגול או...
לא, בשבוע הבא יש רק תרגול. אני אסיים את אני אעשה קוויטי מתוד, ואז תרגול חזרה.
אוקיי. החומר הזה חדש מהשנה כאילו? כי אני לא רואה אותו בשנים קודמות.
כן. ולי הוא חדש מיום רביעי.
וואה.
לא שלח אימייל עם רשימת נושאים.
אוי לא. אז מה אנחנו נגיד? טוב.
יהיה בסדר.
אני מקווה שזה לא יהיה במבחן.
אני לא חושבת, גם אם יהיה משהו, אני לא חושבת שזה לא יהיה משהו, כאילו,
זה לא יהיה,
אני אתחיל לעשות עכשיו פיתוחים.
אני לא בטוחה שהבנתי כל מה שעשית, כאילו באיזשהו לא איבדתי אותך, מרוב שזה, לא יודעת, כזה נחת, אבל...
כן, זה, כמו שאמרתי, זה נושא שבדרך כלל הוא על פני כמה הרצאות, אז אני פשוט חייבת לדלג על הכל.
כן.
זה, כן, אבל בסדר, כמו שאמרתי, זה לא, יש איזה שהם, אני אעשה בסוף סיכום קווים מנחים, מה חשוב.
רגע, ואמרת שאת מעלה את ה...
כן, זה נמצא במודל, ההרצאות של, נקרא אורן רז, בחור מאוד נחמד מוויצמן שמלמד את הקורס.
והתרגיל שבמודל הוא קשור לזה, כי כאילו...
כן, אבל תכלס קשור רק לחלק הראשון של הרפליקה טריק, שכאילו לחשב משתנים אקראיים שמלכים בלוג או משהו כזה. זה משהו שהוא... I think it's been like 10 minutes. right? Just got confused because, yeah. So, okay, so this is what we start from. We have the summation over A smaller than B, and we said that this is like half of taking the summation over A different than B. So, first of all, because A different than B, Q just equal to small q. So we have Q over 2, and then summation of A different than B, sigma A, sigma B. Now, we can take this summation and this little and say that this is equal to summation of all A and B minus the summation of A equal to B, because we already took Q outside, so this is just this sum now. So this is going to be equal, let's try to explicitly. So A and B minus A equal to B. So this is just going to be two different summations. So we have sum of sigma A square, because they are independent, minus sum over A of sigma A square. So we have the square outside and inside the sum that we had for infinite. And because sigma equal to plus minus 1, so sigma square equal to 1, then this is just n. Right? A go from 1 to n, so this is just a constant. Then overall, this is equal to Q over 2 sum over QA square minus n. Okay, so we got rid of most of the summations, some of the summations, all of the summations that relate to Q, and basically what we want to do now. So, okay, so now we have we still have the trace that we need to take over all of the different states, but now it's look a bit more similar to what we had for like the normal ferromagnetic case, where we just have summation of sigma I square. So we still want to get rid of that expression, so we're going to do Hubbard-Satonovich again and define a new variable. And but this is just a mathematical trick, so this is not going to give us like the order parameter. So we had another integral here, and basically after that we get something that's linear with the summation, so we can take the trace. So I'm just going to write the expression after that, because I don't think you need to pay attention. So overall, Zn is equal to 1 over n theta log 1. So this is already the energy. Okay, so this came from the trace. This is the same trace that we took for the ferromagnetic case, so we should be able to together. And this is from the Hubbard-Satonovich thing. So this is the free energy overall. And then, if you remember, the whole point was that we calculate Zn, and then we take the limit where n go to 0. So this is what we want to do now. And if we take n go to 0, we use use the limit of log. This is not interesting, so lim of n go to 0 give us, so this is, let's call it fn. So this is going to give us 1 over beta, an integral dz over square root of 2 pi e minus z square over 2, and then hyperbolic tangents, and then log of 2 cos. This would be cos 2 beta z square root of q. Now, if we take, so this is the free energy, this is the total free energy after everything we did. And now we want to find the order parameter, so we know the order parameter minimize the free energy, so it should be the solution of that. So you see that, did I forget something? Yeah, I forgot something, sorry. Minus beta 1 minus q square over 4. So if we take the derivative of all of that, so we're going to have something that go like q in here, right? 2q, and we're going to have some integral here that depends on q, because we can't isolate q completely, and then we get eventually like a closed equation for q. So this is what you got in the lecture. This is tanh square beta z square root of q. And if you want to find a specific value of q for specific value of the temperature, right? This is 1 over the temperature. We just need to put the temperature and solve the integral and then isolate the q. So super fun. But you know we usually solve like that type of equations. We usually just plot like the right hand side and the left hand side and compare them. So if we do it here, we see that. Okay, we stay with the blue. So the left-hand side is just q, right? So let's give us something like that. And the right-hand side, okay, I could really use some colors, so I'm just going to do like 3 different figures. So if the temperature is higher than the critical temperature, which is 1, we didn't got it, but I'm just telling you, then you're going to have then all of that, which we call it, let's call it f of q. Then f of q going to be something like that, like saturated, like, okay. If T is equal to the critical temperature, it's going to be something like they both start at the same point, something like that. Like they don't cut each other at any point except of the origin. And if T is smaller than the critical temperature, then we have something. I'm sorry, I'm very bad at that. Okay, let's do first that and then that. So they cut at one finite point. So we have some value that depend on the temperature. So overall, this gives us Q is equal to the order parameter equal to 0 where T is larger than the critical temperature, and some function of the temperature when T is smaller than the critical temperature. So what this is basically just a phase transition in the way that we know it. Like, you know, when we solve for like even like 2D Ising model, right? We had the order parameter and the temperature when we had like that. So this is what we got here. Okay, so this is basically the replica symmetry, and the consequences is we get second order phase transition as we may or may not expect. But there is one tiny problem, that all of that is wrong. So what happened is if we look at like a normal second order phase transition, we had something like that, and then for like T larger than the critical temperature, and then we go to something like that, where T is lower than the critical temperature, and then we get the symmetry breaking between the two minima of the system. But if you look at what happened here, so the way that you can see that this doesn't work, like you can calculate apparently the entropy, and you get like a negative entropy and all kind of stuff that just are not physical. So this doesn't work. And if you actually look at the system, what happened is that in high temperature you get something like that. You go to a lower temperature, you get something like that. And then if you go to even lower temperature, this is start to look like more and more detailed. So you're going to have something like that. Like, I don't know how to draw it, but you see you have a lot of like more minima on top of the big minima. So you actually have phase transition in every temperature that's smaller than the critical temperature. So instead of have transition at T equal Tc, you have a transition in any temperature below Tc. So the lower the temperature, the more details you're going to see supposedly in the free energy, and you're going to just jump around between all of these points, and you're never going to get to a stable state. So, which is the thing that defines the concept of spin glass. People said it like, I think Stas said it once, that like glass is like liquid, because you always like, it's like a fluid or something, never mind. So you see that like you never get to a stable state, unlike the case of a magnet where everyone just gets to one minima, and that's it. So we're not going to solve further than that, because this is already like too much, but you can go like to do like people say like, oh, you can divide a system into like subsystem, and then each one of those systems have like one specific order parameter, and then you can define like more and more corrections to that. But yeah, the whole point is just that the real picture is more complicated than what we actually can solve. So this is physics. Anyway, and with that optimistic conclusion, we finished.